Okay, so welcome again. So today we're going to look at the properties of pure substances. So before we start, let's do a little summary of what we have covered so far. So far we have studied the first law, which we wrote under this form, okay, where the change in energy could be equal to the change in internal energy plus the change in kinetic energy plus the change in potential energy. Okay, in most cases, the kinetic energy can be ignored and the potential energy can be ignored. So we say that Q minus work equals to U2 minus U1. Okay? Then we did see that for an ideal gas, the change in internal energy was equal to mCV delta T, or which is the same mc sub v dt. Okay, so why is this possible? Because if you remember, we said before that a substance is defined by its properties, and the states of a substance is also defined by its properties. So in other words, when water is in ice state, it will basically have the same properties all the time. When ice is in liquid state, the properties will be more or less constant. And when water is in gas state, they will basically have the same properties. Okay? So basically, since an ideal gas is always on the same state, we can say that the property specific value will not change. Okay? And here we say this will be constant. All right? But really, CV in most cases, in the general application, is in function of the temperature. All right, so in other substances which are not ideal gases like the water, we know water can go from state solid, ice, to let's say gas, going through the one where it will be a mixture. So in that case, the value of the CVs and other properties of the fluid will not be the same at all. So how do we know what is the state of a substance is the goal of the video today. But before doing that, I'm just going to do here, this figure is not that important. It's basically just to show that we have the pressure temperature diagram. Okay, so if we look, if we do a line like this curve is completely junk, doesn't mean in real life it looks this way. But basically, if you look at these two lines, we can say, for instance, that on the right hand side of this line up to a point called the critical point, you will have vapor over here. Then this will be here gas, so vapor over here, gas over here. Then we're going to have liquid over here and solid over here. Okay, so basically you see different states: solid, liquid, vapor, and gas. And this point here actually is what is called the triple point. Okay, you could find a substance in three different states that will be vapor, solid, and liquid. Okay, and CP we call is the critical point. Alright, so this figure, for example, to give you one example, okay, so for example, what is the fastest way to get ice? Do you first need to get liquid? Can you go from liquid to solid ice, or it would be faster to go from vapor to solid? So you can see you can also go to vapor water to solid, and actually it's a lot faster, because If you go here, if you cool it down the vapor, you cool down to liquid, and then you keep cooling, you get to solid. But now imagine that it's very cold outside and you just boil water. What will happen if you take all the boiling water outside and you see the steam coming out of the bowl going into the cold air? It will be transformed right away into snowflakes or little cubes of ice. Okay? All right, so now we go to the important part for the class, which is what is known as the TV PV diagrams. Okay, so you don't have to do both figures. You can do either one. They're just going to give you the same information, but sometimes one can be easier than another one. So let's start by the TV. So T is temperature. Letter V is specific volume, because generally in the tables you will find a specific volume, but it could also be the volume. Okay, and let me just do the other figure now. P and V. Okay, so over here you do like a general curve, sort of like this. Okay, and now, so how can I explain this? Okay, so if you remember the equation PV equal RT, here we have three variables, T, V, and T. So basically when you do a figure T and V, you only have two variables, but we want to introduce a third variable. So what happened over here, this will be the two variables that you fix, that you can vary. So you need to also define a variable that you can vary. So for example, if you have the TV diagram, the variable that will be constant will be the pressure. And for instance, we'll have lines that would go like this. So P1 constant. We can have all the lines going this way. P2 constant. Okay? And these lines go from lower to higher. On the PV diagram, otherwise, you have P and V that can vary, so the one that needs to be constant should be the variable T. Okay, and see over here, actually, that these lines over here are constant. All right, so what can we add over here? So in this case, in this side over here, you have gas if you go far away. Otherwise, this area will be superheated vapor region. This region over here will be liquid, and here in the middle will be a mixture. So the same thing over here, liquid, mixture, and gas. Okay, so the point over here at the top of each one will be the critical point. Okay, and now what's important is that the line from the critical point on the right hand side will be the saturated vapor line, and on this side over here from the critical point to this side should be the saturated liquid line. Okay, so why is this so important? It's because the only difficult thing really about thermodynamics is to use the tables. The only thing difficult is because sometimes you don't know which table to go get the information. So these figures will tell you, for example, if you know the temperature, the volume, and a certain pressure, you can find if the state of the substance is a mixture, it's a liquid, or it's a gas. Okay, and you can kind of do the similar thing over here. So what's specific about the mixture, let's think about water, is that a certain quantity of water will be in the liquid state, but another quantity of the mixture will be in the gas state. Okay, so because of that, we need to define a variable, which we do on the next page. Which is x, which is known as the quality factor. Okay, and what x is the amount of vapor or gas divided by the total mass. So that means the mass of vapor plus the mass of liquid. Okay, so sometimes this is written as m, g for gas, mg plus m instead of liquid. Sometimes they use the letter f for fluid. So basically it's a percentage of gas within a mixture of vapor and liquid. Okay, so now let's say you want to know what is the specific volume of a substance. So that will be equal to V fluid plus X of V gas minus V fluid. Okay, so that would be the specific volume, but you can use the same equation for other properties, like let's say the internal energy will be equal to U fluid plus X U gas minus U fluid. Okay, another variable we haven't studied will be, for example, the enthalpy will be the same thing. And another one we haven't defined yet is the entropy. Minus S fluid. Okay, but I'm not too worried about this because by doing problems it will become clear. Okay. Okay. Now one more thing, and I will stop over here, and that's related again to either one of the figures before. Can be the P or TV. I'm just going to do these curves over here, where this point here was your critical point. This line was the saturation vapor, and this line here was the saturation liquid. Okay, so very quick over here. If you remember on the first page, we said that because of the ideal gas is always in the same state, the value of the property CV can be more or less constant. Okay, so that's for what is known an ideal gas. There is something that I like to call an ideal substance. So for example, let's say the substance you are studying is far away from the saturation liquid or far away from saturated vapor. In those cases, when you are far away, you could treat the substance again as an ideal gas or ideal substance. Okay, when in this area or this area. And sometimes in the textbook they like to look at so if it behaves as an ideal gas, we have the relation PV over RT that is all the time satisfied, okay? Which is the compressibility factor. If this is for an ideal gas, we have that PV over RT equal to 1, which basically means that it behaves like an ideal gas. So we can say that if you move far away from the saturation vapor line or move far away from the saturation liquid line, okay, you could almost assume that that substance behaves like an ideal gas. And in some problems, it might just make it easier. Okay? So again, Z over here is the compressibility factor. Which basically is just a factor that indicates how close it is or how far it is to behave as an ideal gas. Okay? So I'll stop over here for this video. Thank you very much.